We usually think of cryptography as this invisible thing, right? A shield that's protecting our data in the background. But what if we could actually hold that shield? What if we could build a physical box that takes all that abstract math and gives us a concrete, real-world yes or no on whether something is authentic? Well, that's exactly what we're going to talk about today.
And this really gets to the heart of the problem, doesn't it? I mean, we live in this world of deepfakes and digital copies that are getting scarily good. We literally can't always trust what we see anymore. So, the big question is, how do we build a system of proof that doesn't depend on our eyes, but on something, well, something rock solid and fundamentally trustworthy?
Okay, so here's how we're going to break this down. First, we'll look at the whole digital signature problem. Then we'll see how you turn that math into actual code. After that, we get to the fun part, building the authenticator. And to wrap it all up, we'll explore what this whole idea of a black box for truth really means.
All right, first things first. Let's get one thing straight. This is super important. We're not talking about encryption here. Encryption is like putting a secret message in a locked box to keep it hidden. What we're talking about is authentication. Think of it like the old-school wax seal on a letter. It doesn't hide what's inside, but it proves without a doubt who sent it and that nobody has messed with it along the way.
So yeah, a digital signature is basically the modern version of that king's seal on a treaty. It's an unbreakable, mathematical mark of who it came from. The key concept here is something called non-repudiation. It's a fancy term, but all it really means is that the sender can't turn around later and say, "Nope, wasn't me." The math makes it impossible to deny. It's a promise baked right into the code.
So how does this magic actually work? It's basically a four-step dance. Step 1, you take the message and create a totally unique digital fingerprint for it. That's called a hash. Step 2, the sender takes that fingerprint and signs it by encrypting it with their private key. Now on the other side, step 3, the receiver uses the sender's public key to unlock that signature, which reveals the original fingerprint. And finally, step 4, the moment of truth. The receiver hashes the message they got and compares it to the one they just unlocked. If they match, boom, you've got mathematical proof it's the real deal.
Now, this whole process is really elegant, but it is also incredibly strict. I mean, if even one single bit is off, the whole thing just falls apart. And let's be honest, we humans make mistakes. So for this to be reliable, for it to work perfectly every single time, you just have to take the human element out of it. And that is where code comes in.
All right, so let's move from the math on paper to actual working code. We're going to take all that theory and bake it into a program a computer can just run instantly. This is where it gets really powerful. And the best part is, you don't have to be some cryptography genius to write this stuff from scratch. Nope. Programmers use standard, pre-built libraries like HashLib and Python to do all the heavy lifting. The script itself is pretty straightforward. You give it a message and a private key, and out pops a signature. And the verification part, even easier. It just takes the message, the signature, and the public key and spits out a simple answer. True or false. A digital thumbs up or thumbs down.
Okay, this is where it gets really cool. We've got the theory, we've got the code. Now, let's give that code a body. We're going to build a physical home for it. A dedicated little device with one single purpose, to run our script and give us a crystal clear, unmistakable answer. And you might be surprised at how simple this is, conceptually. You really only need 3 core parts. First, you need an input, some way to get the data into the box, like a keypad or a sensor. Second, you need a processor, a little brain, like a Raspberry Pi, to actually run the code. And third, you need an output, a simple way to show the result.
And that output is the whole point. All of that complex math, all that cryptography, it all boils down to this, a simple binary verdict. A green light says, yep, the math checks out, the digital fingerprint is a perfect match. A red light says, whoa, hold on, something's wrong here. The message was altered. There's no gray area, no maybe. It's just yes or no, verified or tampered.
So, we've built our box. It's got an input, a brain, and a light. But what does it really represent? Because it's so much more than just a pile of electronics. It's really a kind of black box for truth.
Yeah, this quote just hits the nail on the head. You could think of it like an airplane's flight recorder. You don't necessarily need to know exactly how it works on the inside. That's the black box part. Its function is dead simple. You put a claim in, and you get a verified result out. It doesn't have an opinion. It doesn't have a bias. It just reports the facts based on the math.
And this simple idea is the absolute foundation of what we call trustless systems.
These are systems where you don't have to rely on trusting the people involved. With a device like our Authenticator Box, you don't need to trust the person who gave you the message. You don't need to trust their story or their reputation or anything about them. The only thing you need to trust is the math.
So let's bring it all home. As we dive headfirst into a future that's going to be flooded with perfect AI fakes and misinformation so good it's impossible to spot, our own senses are going to become less and less reliable. So you have to wonder, in a world like that, are these simple, dedicated devices, these little black boxes for truth, going to become our last line of defense? Will a simple green light be the only way we can be absolutely sure that something is real? It's a heavy question, but one we definitely need to start thinking about.